sound. I will not. I hope this will be, yeah, this is better than crying one. Okay, so in principle or in practice, I should have started the X-ray emission processes number 2, part 2. But yes, recap from the, no? Okay. Oh, I'm sorry. Access my talk in a reverse order. Okay, so this is where I had stopped. So I had stopped showing you emission, dominant emission from cooling hot plasma, which shows a lot of emission lines, and basically coming from photoionized or collagenally ionized plasma. So today I will just show you some quick recap what I have missed from that day. So, okay. So whatever I am talking about has been taken from 2 references, radiative processes in astrophysics by Rybicki and Lightman. You people are familiar with this book, and most of you are already familiar with high energy astrophysics book by Malcolm Langer. And another reference I should mention, I have followed a lot of lectures by Professor Dipankar Bhattacharya from Ayuka. Okay, so we had discussed a lot about emission processes. Now I am coming to something called photoelectric absorption. Basically, I mean, you might have you have already heard about this term quite a few times by many of the lecturers. So this is about absorption due to presence of some neutral neutral molecules which are present in the midway between you and some X-ray source. So X-ray photons passing through this gas, these molecules, and then you see absorption, and due to expense of some electrons which are ejected from the medium. So it's called photoelectric absorption. So you know photoelectric effect. So you know there is a photon which is interacting with the material, and then a photoelectron is ejected, something like similar. So why it affects us? You can see in this cartoon that this dashed line presents a power law spectrum, which is like a power law spectrum from the X-ray source. And due to the presence of this kind of absorbing material which can pose this photoelectric effect, and you can see there are a lot of kind of loss of photons which you detect. If you do not consider for correcting this absorption, you cannot predict the properties of the source. Yeah, please.
What is the gray region and what are all the narrow lines?
Yes, gray region is basically you can see this is this dotted line is actually intrinsic spectrum which you should expect. This is theoretical spectrum which you should expect if there is no absorbing material in front of you. If there is a absorbing material in front of you, this is why you do see these kind of absorption features. This gray region is actually kind of you see this is touching to the this intrinsic spectrum. So this is basically kind of telling you what you expect if there is no absorption. Yeah. So some of the examples of this kind of spectrum, this is from some SNR, Cassiopeia. You can see there are many lines and then continuum as well. So switching to rapidly to other sources, this is another supernova remnant where you can see multiple lines here. This is E0102. Why I'm showing you here? Because many of the astronomical sources in which we can, and if we can develop an understanding of emission processes, and also if we can know like exact line positions, we can use them as a calibrators. They are used as a calibrator, and this is one of that IHEC is putting a lot of effort to develop this source as a calibrator for medium resolution spectroscopy. Okay, coming to another part which you have already heard of even today morning, X-ray absorption. In case of X-ray absorption, what happens? The photons are interacting with material and they are absorbed. And with the expense of, like, there is a excited state of that atom or molecule or ions, and photons, and I mean there may be fluorescence spectrum at lower energy, or you may have a Auger electron ejected, or both. So, but story is like you will lose photons from your incident X-ray spectrum. So at that particular energy. So this means there will be a dip in your spectrum, and that you can expect as a power absorption spectrum, or absorption line, or absorption edge. Where you expect such cases, one such example is like these are called warm absorbers, and like a lot of ejecta from AGN center can absorb, and their understanding of absorption features gives you understanding of the dynamics of ejected material from AGN core, or from in the AGN surrounding. Another example is like you can, I mean, you have heard, if you want to understand composition of ISM, you need to know properties of absorption. Okay, this is already shown in one of the lecture. Another example of AGNs, you can have in certain cases, you may have edge-like structure, absorption edge. These are called absorption edge. Absorption edge is also seen in due to instrumental effect. For example, if you, I mean, maybe by this time you have already seen X-ray spectrum from NuStar or XMM. In XMM, you will see there is a edge-like feature. Your spectrum is decreasing very rapidly at around 2 kV or something. That is due to gold edge. Yeah.
Are we seeing a P Cygni profile there on the right? What
Yes.
are we?
Yes.
Okay.
Yes. Okay. So it was it's a surprising spectrum for a blazar, mercurium 421. In case of blazars, you expect only power law, but here we have seen, we can clearly see there are carbon edge absorption feature as well. Okay, so not related to processes, but this is also, I had showed you some beautiful emission from different objects. This is one such a beautiful picture provided by Chandra, X-ray SAAO of Titan. In sometimes in 2003, Crab and Titan were occulting XMM Newton. So XMM Newton, Titan, the Jupiter's moon was in between Crab and Chandra, and Chandra had clearly seen a shadow of that. This is one very beautiful picture for now. Switching to this really part 2, continuum emissions. Okay. Generally, production of X-rays, basically in continuum emission, are from very hot gases that you have seen, like millions of Kelvin, and that they, I mean, apart from these photoionized or collagenally ionized plasma, you may have thermal Bremsstrahlung emission or black body radiation, which are falling in X-rays. And there may be a cases when we will be getting emission due to motion of relativistic motion of electrons in presence of electric field or magnetic field. Then Compton is scattering of low energy radiation field, which are upscattered to energetic by energetic electrons in the medium. So these are called inverse Comptonization. So these are a few topics I will be briefly talking about during this talk. Okay. So whenever we are talking about radiation due to acceleration of some of the charges, the easiest treatment is like to start with electric field and magnetic field. These are the expression of some charge which is moving electric field and magnetic field due to motion of some charge. So these are these are pretty standard equations which we have seen many times in our college days. So in order to estimate the or to get a feeling of loss of energy and radiation as an output from an accelerating charge, one can use two kind of approaches. One is by Thomson treatment. I've just copy pasted it from Longueur. It's really a very beautiful statement, which says like how you can expect pulses of radiation from a deaccelerated accelerated charge particles. So I decided to avoid that long reading that long text. But if you do very simple calculations, yes, very simple ones, which is always recommended by us or anyone who is talking about these. So basically, emitted power can be calculated in terms of pointing power, pointing flux, and it is basically expressed in steps. I admit that. But one thing is like the expression emitted power is actually proportional to the modulus of a acceleration square. So, okay. Something similar, but expressing the same end expression in terms of magnetic moment rather than acceleration. So P double dot is basically the magnetic moment, and if you can express those in terms of that. Okay. So from this, the total radiation rate is given by Larmor's formula. And we have noticed that in this formula, the acceleration is expressed in proper acceleration. Whereas the charged particles in relativistic sense, that radiation loss rate is measured in instantaneous rest frame of the particles. And if you make a polar diagram, which I will come a bit later, you can see that distribution is distribution of photon field in the form of dipolar form. And radiation from a single accelerated electron will always be polarized. And actually, I will be coming to that point again shortly. Another approach is like using Maxwell's equation, which we are familiar with. So basically, these are the Maxwell's equations, and after some very simple simplifications, not so simple, yeah, you can get a term like this, equation like this, and if you really solve it using some clues, tricks, and you will get expression for electric field, and you can see that it's also proportional to the acceleration. Okay. And here, the idea is like you use Maxwell equations and involve writing down certain retarded potentials for electric and magnetic field, and for some distant position away from maybe r distance from the central position of the accelerated charge, you can get this expression. Okay. Yes, somebody had made this joke. So God provided Maxwell equation and for electromagnetic radiation. Yes. Okay. So you may have a relativistic case and non-relativistic case. Till now, we haven't included any included relativistic factors in our acceleration. So in case of relativistic motion, you can express your acceleration vector in terms of 4 vector. So this is basically 4 vector, and you just plug in those expression of this acceleration term in the formula which we derived for using either J.J. Thomson's approach or Maxwell's approach. You can get to this expression, and obviously again simplifications, and we know that the loss in energy will be actually Lorentz invariant. So you can get this beautiful formula where you can split acceleration term into 2 parts, perpendicular to your direction of motion and in parallel to the direction of motion. Okay, so I was mentioning about this pattern. So difference between relativistic and non-relativistic case would be that the radiation pattern will be skewed in the direction of motion if you are your charge is moving with a relativistic motion. So that is called beaming effect, relativistic beaming effect. Okay, I mentioned that polarization from for a single accelerated charge, I mean, emission for a single accelerated charge will always be polarized. So what matters, like if a collection or population of charges which are moving with some I mean accelerated, and if collection of the emission is polarized, then we call it a polarized emission. So for example, radio polarization observed from radio using radio observations or optical observatories. And then yes, we have seen X-ray polarization observed by XP integral and astrosat. Okay, how many of you know what in mathematical terms what is spectrum means? You have seen a spectrum as a plot. X-axis is energy, y-axis is some sort of flux, integrated or differential. This is called a spectrum. But in mathematical terms, a spectrum is basically Fourier transform of electric field of that moving charge, for example. So if you have gained some kind of experience, you from the talks, from your own hands-on sessions, you know that there are two kind of spectrum we have seen so far. One is like the number of photons with energy follow a particular distribution, Maxwell-Boltzmann distribution, that is called thermal distribution. And you may have deviation from that, and that is called non-thermal, non-Maxwellian. And one such example is power law. Okay, we'll be talking about all these in one or different way. So, but you have seen that in astrophysics we have certain certain sources which emit radiation. They are the source of radiation. So you have a sources where you get photons which are actually generated, and you have sources or intervening medium where you see absorption. So whenever you are dealing with radiation coming from certain source which is passing through intervening medium, you have to deal with both two kind of processes, that is emission and absorption both. So this is basically, this comes under radiative transfer equation. This is called radiative transfer equation. Alpha nu is basically the absorption coefficient, and J nu is basically the emissivity or emission coefficient. So then if you do certain jugglery in mathematics, you can express it in terms of SV, which is basically source function. Source function is basically ratio between v divided by alpha v. So it's like a ratio between emissivity and absorption coefficient. Okay, you can ignore this. Okay, any electromagnetic radiation from quantum mechanical point of view, any electromagnetic radiation arises from transition between labels of different electric or magnetic moment. It may be transition between two bound states, which we have seen that is the applicable in terms of explaining the line emission, or maybe between continuum and free states. So why I'm showing this, because it is applicable to explain the emission from the population inversion, which are basically Maser emission. And one can go to details, and also this is effective mostly in microwave band, not in X-rays band. This is why I'm not going to very detailed of that. Just wanted to mention you that there are popular inversion processes like such as Maser, which are playing role in astrophysical environment as well. Okay. After slight deviation from what we wanted to discuss, like for example of thermal and non-thermal, I came back again to the black body radiation. This is basically intensity, which is expressed in terms of Boltzmann, Maxwell-Boltzmann distribution. So idea is like if temperature of your system is less than the temperature of the background, then you will face absorption. And if temperature is greater than background, you will face emission, continuum emission. Okay. So this is how black body radiation looks like. At large optical depth, thermal source will emit black body and emission will be received from photosphere, for example, in case of stars. And optical depth is a frequency dependent. Source could be optically thick for some frequencies and optically thin for other. And we have seen in case of sources like certain the radiation in certain frequencies are lagged even if they are produced by same emission processes, maybe due to the effect like the radiation was originated from a region which was optically thick for one particular frequency range and optically thin for other frequency range. Okay. One such examples which we have seen many times in this workshop, thermal emission from accretion disk. Accretion disk in black hole X-ray binaries, accretion disk from AGNs. Dan has talked a lot about that, and even Jack has talked a lot about that. Okay, this is one such example, Cygnus X1. This is, you can see that clearly disk is basically a black body radiation, and you can see there are other components which we'll talk later. Okay. Once we have discussed like, okay, so particle is accelerated and moving, and then you have emission from them. When particles are interacting with fields, then they lose energy, and that energy is emitted in terms of in the form of radiation. One such process is called Bremsstrahlung, that is also called known as a free emission. So in this case of an electron is moving in an electric field or in a presence of some nuclei, then it loses energy and you get radiation. So this is a simple expression. Yeah, very simple one. So if you have a population of electrons, maybe a population of electrons which are moving in a electric field, then you will have a if you estimate emission from all the population, then you will have some shape like this. So if the population is like thermal, population of those energetic electrons is thermal, then you will have thermal Bremsstrahlung. If it's a non-thermal, following non-thermal population in this to start with, it will be non-thermal. Okay. Where you see these kind of processes at play, this is one example. Example is from the cluster. Basically, this is simulated spectrum for GRISM. So this continuum emission is contributed by two processes. One is like the AGN, which is sitting in at the center, and second is actually Bremsstrahlung emission. Second case may be the charged particles are not moving in an electric field, but in a magnetic field, in the presence of magnetic field. And you know that if the motion of charged particles in the presence of magnetic field is relativistic, if electrons or positrons are moving with the relativistic velocities in the presence of magnetic field, they will lose energy and generate emission, which is the process known as synchrotron process. In case of synchrotron, you will see basically non-thermal emission. Emission is most polarized. Another case may be that your electron, okay. Another case is like if particles are following a curved magnetic path, a curved trajectory in maybe in the presence of very strong magnetic field, which is seen in case of pulsars. So you see loss of energy in the presence of, in these cases due to curvature process. This is called curvature radiation because, yeah. So we have come across about, the spectrum which does not follow Maxwell-Boltzmann thermal distribution. We see that is like a power law. And power law, in case of power law, basically if you plot your intensity and energy in log scale, it will be basically a straight line. Okay. So it is characterized by like some I proportional to some kind of frequency power, some alpha or minus alpha. Alpha will be index. Okay. So, but nature is not as simple. In case of all the synchrotron emission, if you think like synchrotron emission should follow a power law, and you should get emission is starting from some 0 to infinity as following this power law. No, nature is slightly different. So you get certain kind of absorption that is like synchrotron self absorption. No, yes, then you see that your electron population cannot be infinitely energized. It cannot have a energy starting from 0 to reach infinity. So it will have some kind of cutoff. So you get cutoff in synchrotron spectrum. Okay.
Does the same apply for inverse Compton scattering?
I'll come to that point. But yes, in case of inverse Compton scattering, you have energetic electrons or particles, ultra relativistic particles, which are interacting with your photon field, and they are actually giving their energy to photons, and photons are gaining energy. So basically, there also, because you cannot have electrons energized infinitely energized. There will be I mean, the more energetic electrons will cool rapidly. So there will be a limit when electrons will not have sufficient energy to impart to seed photons. So you will have a cutoff in inverse Comptonized spectrum as well. So basically, this is one thing which I wanted to talk about. This is in this scattering process, basically low energy photons are gaining energy from electrons. And why it is called inverse Compton? Because in Compton we know that electrons or particles are actually giving energy to photons, and photons gain energy, electrons lose. But here it's inverse, because electrons are giving energy to photons, low energy photons, and photons are energized. And you see a lot of emission from blazars falls actually in this energy band. And this is, and also I mean, here electron population and seed photon population are involved. So the observed spectrum is dependent on both kind of properties of the seed photons and properties of the energetic electrons. Depending upon the origin of seed photons, you may see different kind of spectrum. But in many blazars, when we get some components falling in X-ray band, that is self-synchrotron component. Why I'm mentioning all this, because I work in blazars and try to model these processes using multi-wavelength observations. Yes, this is something called Klein-Nissina cross section. Yes, it is mostly applicable in gamma ray band, where there is a deviation from Thomson cross section, and then we use this for gamma. Okay. So again, yeah, this is more applicable in blazars. Okay. So this is one example from some binary X-ray pulsars, where you can see that almost all kind of continuum processes are mentioned: Brahms, cyclotron, black body, and line emission. I will just briefly mention some of those processes which are frequently used to model the spectrum in X-ray band, spectrum from AGNs, spectrum from X-ray binaries, and even stellar sources. One of the such processes like thermal Comptonization. And Andrzej Zajaski has done a lot of work on these thermal Comptonization models. So this is how non-relativistic thermal Comptonization spectrum will look like. I'm going so fast so that you can have more time for next class. Yeah. So if it's saturated, then it will look like this. Okay. There is something you have already heard about, like Compton reflection. So if your source is I mean, if your high energy photons are reflected from accretion disk or some kind of plasma, then you will have this kind of effect, Compton reflection. In case of you can see in case of Thomson and photoelectric. So this you have seen, like if there is a Compton reflection present in your source, you will have a spectrum like this. You expect a hump due to in hump and several lines in low energy band. Okay. So yes, whatever all these, I did not want to make life more complicated, and so how to get I use these models for your analysis and all. XSpec is actually rich in already enclosing a lot of models already available. So you can just call, for example, disk BB, disk black body, and all those. You can, and best way is to go to the details of those models and try to see what are the implications of parameters, what is limitations and all before using it. Yes, there are multiple processes which I have just briefly mentioned. Continuum, which are like black body synchrotron BRAMs, or scattering process, for example, inverse Comptonization, and lines, for example, charge exchange, fluorescence. And these things can be seen in like solar wind, comets, fluorescent, solar corona, or soaked plasma, for example, in SNRs, or galaxy clusters, or accreting compact objects, then collimated jets, for example, in radio galaxies and blazars. Okay. I'll stop here. Thank you.
Go back to the models. Yes. Okay. I just want to know, is there a model that you could use for maybe blazars, like a model that works for blazars or that works for AGN? Like, if I use this model, I'm sure that I'm going to get a good fit.
You asked that if there is a model available for blazars and AGNs. So basically these models are, in case of AGNs, you have different components, I mean different physical components which are contributing to the total radiation. So for example, in AGNs you have disk, which will contribute in which will be emitting in using thermal processes, basically black body, and emitting in for XRBs emitting in X-rays, and for AGNs it will be emitting in UV. Then you have corona. You have corona will be emitting in X-rays. So corona will be emitting non-thermal emission. Then you have, you know that from Dan's talk and Jack's talk, like there will be reflection. So you need to include reflection from the coronal emission is reflected by the disk, and you get reprocessed emission from the disk. So there is not a single model which just you can just call it and start fitting. But in order to model is AGN spectrum in X-ray band or combined UV and X-ray, you can incorporate these models, for example, black body, Comptonization, or power law, or reflection model, for example, RELXL. You can call them in a combination of your choice or your comfort, which can best represent your data. So yes, there is not a single model. Same for blazars. Unfortunately, in XSpec, we do not have any a model for IC component or synchrotron component. So in case of modeling the emission coming from blazars, we have our own versions of codes with certain simplifications in calculations, or in using very simple approximations for the very complex integrals involved in IC and in other interactions. So this is why we develop our own codes, for example, leptonic, hadronic, leptohadronic, or you may have, I mean, you may have any flavor of those. Yes.
Now, when it comes to fitting multi-wavelength data, do you have to write a code or you can still use expect?
It's kind of, I will reiterate what I said. It depends upon your source. If you know your source exhibits certain kind of physical mechanisms or certain kind of, then you can use like combinations of black body, power law, Comptonization, or whatnot to make a consistent model, for example, in case of AGNs. But yes, in case of blazars, we do not have any axis spec model available which is well accepted by users. I can mention there is one model which Pranju and her collaborators had developed for specifically for blazars, and especially for time independent model, like including synchrotron and Comptonization and all that, including disk and torus, everything. But that is still very, very simplified version of the story which blazars exhibit. So it's like a kind of a kids in a like a childhood stage of modeling in XSpec. Yeah.
In fact, I have a question on the question. Was your question on the existence of multi-wavelength models or on whether an optical spectrum can be read and fit in XSpec?
Yes, I'm considering a situation where you want to model from maybe radio to gamma ray. So I'm wondering if there is any single model that can do that, or you have to write a code for it.
Now, the reason why I'm mentioning that is I'm giving an answer to another question, but maybe it's an interesting question. There is a way of allowing XSpec to read multi-wavelength data. An example of that is in the XSpec thread of SAS that shows you how to read the optical monitor photometry point in XSpec and fit them with a model. It's in fact a very simple concept. If you have photometric points in any wavelength, you can define a diagonal unary matrix, and you can treat the photometric data as a spectrum with an effective area of 1 and no redistribution. And if you do that, in principle, models like emission of the accretion disk, for instance, in supermassive black holes, you can make multi-wavelength fitting because the models of accretion of supermassive accretion disk, they in principle can be extrapolated to UV, to the optical. Models of Comptonization, for instance, they can be extrapolated into the optical or UV. So this is conceptually possible. And but Sunil is of course right. There is no XSpec does not in general support multi-wavelength models. So if you have a case like fitting from radio to gamma ray of blazars, I don't think you can do it in XSpec. You have to create your own table model and import in whatever software.
Just before that, just want to add I mean, it is about like there is a tool called flux to XSP. It's like a flux to spectrum. So you can use that F tool to convert a range of frequencies and flux combinations to XSpec files, and you could just import and use it. Yes.
There can be
profile basically, but from the energy, what energy, whether it's forbidden or, and whether it belongs to certain kind of transitions which is possible in certain kind of environment. Okay, so energy and property of that transition, whether it's possible or not from the profile. And actually width tells you that some other information, line width tells you some other information, that is like dynamics of the gas which is emitting that particular line.
I have a small follow-up question. The question is that many times the centroid energy, from the centroid energy, we can comment on the ionization state.
Yes.
But the instrument has an intrinsic spectral resolution, right? Sometimes people quote values like there are multiple options within that spectral bin, but they choose one value. Can you comment on that? Like, what is the good practice and how do we know about the exact ionization state?
Maybe it will be good if some expert who is expert in modeling line emission and all can comment on this. Matteo?
Sorry, I was distracted with physiological needs, so but I can still answer the question. Can you repeat the question?
So like for example, we say that the 6.4 is the neutral iron line, but say from iron 1 to 12 or 14, it can be any ionization state, right? So many people comment on the ionization state particularly based on the centroid energy, but the systematics from the error bar of that line does not allow us to say anything, right? So can you comment on good practices about this? Like to quoting numbers and like ionization state based on the centroid energy and all this, because there will be line blending also. Many ionization, like many small Gaussian can come together to show a broader Gaussian, right?
Yes.
So
I'm not sure what to suggest. If your error bar on the 6.4 line is of the order of larger of 0.1 kV, you don't know which is the ionization state within iron 14, I think. So the correct way of mentioning this result is say, I've detected a line whose ionization state, it can be any ionization state between iron 1 and iron whatever you get. Now, that's, that would be my approach. Now, in reality, if you want to measure properly the ionization state of a photoionized plasma, for instance, even in the correct way of doing it is not just relying on one single line, but is relying on plasma diagnostic using multiple lines or using broadband continuum fitting. This gives you an estimate, a quantitative estimate of ionization state. And so I'm not sure I have any better advice than this one, just being rigorous and accurate in the way you describe your results. So saying, I've measured a 6.4 and therefore I've measured neutral iron line is obviously inaccurate, but this is simply because it's an inaccurate way of reporting a scientific result. Nothing to do specifically with X-ray astronomy.
Okay, let me end session myself because we are waiting for another session. But yeah, before that, please come back and we have. Yes, but we need you because it's 4 o'clock and he ended around 4:30.